Welcome to another great O'Reilly webcast. My name is Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's event. Today, folks, we have Paco Nathan with us, and he's going to talk to you about just enough math. Paco is known as a player coach, data scientist who's led innovative data teams building large-scale apps for 10-plus years. As a recognized expert in distributed systems, machine learning, and enterprise data workflows, Paco is an O'Reilly author with his book, Enterprise Data Workflows with Cascading, and new video, Just Enough Math. And he's an advisor for the Data Guild in Palo Alto, California. Paco received his BS and MS degrees from Stanford University and has 25-plus years technology industry experience ranging from Bell Labs to early-stage startups. Folks, we're very excited to have Paco with us today to present this webcast for you all. As we get the event started, I'd like to go over just a little housekeeping to help you get the most out of today's event. First, you'll want to open your group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for Paco. We find that our audience usually has a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for Paco, please preface them with a capital letter Q so we know that they're for him and we can make sure we see it for Q&A. You can also open, move, and resize any of the other widgets. If you would like to tweet from the Twitter widget today, you might need to give it permission to access your account. The Twitter widget will automatically append the event's hashtag to your tweet so you don't have to. And today, folks, our hashtag is OzCon, all one word. If you should have any trouble with the webcast, please take a look at your help widget. If you continue to have trouble, just post it in the group chat and one of our staff will help you right away. If you have any choppy audio or stalled visuals, please try refreshing your window. And remember, the best thing you can do for a good audio stream is close any apps that could interfere. People always ask, so we'd like you to know we are recording today's webcast, and we will have the archive ready usually within 48 hours. And folks, at this time, it is my pleasure to turn the program over to Paco for his presentation. Hello, Paco.
Hello. Thank you very much, Yasmina. I really appreciate the opportunity to present here today. This is Just Enough Math, and getting started on the presentation, let me push a couple of URLs just to have those as background. We've got the links to the video, links to OSCON, and I'll have a few other presentations as well to link. Okay. All right. As far as introduction, this material here, it's called Just Enough Math because it's about advanced math, particularly for a business audience, and the context is to be able to leverage big data. There's a lot of great open source frameworks, and we find that knowing just enough of some of the math that's, say, beyond calculus, you can get a lot more leverage. There's a lot more possibilities. The prerequisites, though, start out at Algebra 2, and we're going to show some brief code examples throughout, well, here certainly in the webcast, but throughout the book and the video, we show brief code examples in Python. Really, you can just cut and paste those if you don't have the background in Python, but we find that it's a fairly accessible language, and we have some resources for it as well. Now, the reason for doing this is that when you look at university math programs, there's generally a lot of requirements for calculus. And frankly, years of this stuff before you can get to the more advanced math that's probably more applicable for big data use cases. And there's probably a lot of good reasons for that. Historically, Cold War priorities on mechanical engineering and the priorities that have changed subsequently, because now in the context of industrial internet, we're seeing huge growth in data, and we want to try to put out there more of a context about how to leverage the open source, how to leverage functional programming, how to leverage abstract algebra, graph theory, etc. So that's what we'll be developing here throughout this material. Certainly this webcast is just in brief, it's a preview of what's available in terms of the video, which has much more extensive background and discussion. There's also the book coming out later this summer, and that has much more in terms of additional material, additional chapters, coding examples. We'll be doing a tutorial based on all of this at OSCON, and then another one at Strata, New York City in October. I've got some links to both those conferences later on here. But it's the kind of thing where you can take your laptop and be able to use the coding examples, work through much more extended discussion. We're also doing full-day workshops throughout the country based on some of this material as an introduction to machine learning. A lot of the rubric that we're using here is based on something called computational thinking. And this is going to be a theme for O'Reilly's OSCON conference. I find it's a very good instructional rubric. It's been promoted through Carnegie Mellon University. And the bottom line there is if you think about the essentials, reading, writing, and arithmetic, then let's add a fourth one in terms of computing. CMU has done created some excellent materials based on this. Google has also presented some excellent materials, a lot of free materials for, say, secondary education teachers. There's a couple of links here for that, but I definitely recommend checking it out. In terms of our approach, leveraging computational thinking, we're going to use 4 parts here. Number 1, the notion of decomposition. When you approach a complex problem, can you break it into smaller, more solvable problems? Number 2, pattern recognition. When we're looking at these kinds of complex problems with big data and math, can we identify when some kind of use case is indicated? Number 3, abstraction. Can we generalize? Can we move from the patterns that are being recognized and be able to generalize strategies? And then number 4, can we articulate those strategies step by step, kind of as recipes for how to handle complex problems? Now, the benefit of that is that this is a structured way of conceptualizing the problem, and it really works well in a team context. It's partly for taking personal notes about how to solve problems, but it's also to be able to convey those notes to other people. And then, as well, that works pretty well for being able to convey to the computers, if you will, in terms of software requirements and algorithms. At the end of the day, it's about building high ROI apps for big data. Now, in terms of our background here, I've got a dual background. On the one hand, quantitative, on the other hand, in distributed systems. And I spent a lot of time in software engineering, but about 15 years ago, those two fields came together. We're calling it data science, big data these days. I led teams building really large-scale apps. For the past couple of years, I've been involved evangelizing open source projects and doing a lot more consulting and training. My co-author is Alan Day. He's principal data scientist at MapR. And Alan has a PhD in human genomics from UCLA Med Center. He's also an expert in big data. He's kind of like one of the crossover points between genomics and big data. And currently based in Singapore, a lot of background in scientific computing. Also a pretty good stage magician. Let's see, I'm going to click over here. I see some Q&A coming up. Try and get the links going. Now, there is some requirement for using Python in terms of the examples, but really you can just cut and paste those. We're going to keep it down to very small morsels of Python. If you want to install that on a laptop, we highly recommend using the free Anaconda download from Continuum. It just makes the installs and packaging much, much simpler. And also there is a great video by Jessica McKellar called Introduction to Python. There's also Alan Downey's work, Think Python. I highly recommend both of these, very accessible. And throughout this work, we're using a case study, a fictional business that we've come up with. And the notion is that you can go onto a tablet and order some cocktails, the bartenders create them, and you've got drones that deliver them right to where you are. So we're calling this company foobartender.io, and it's a rich context in which to come up with some good use cases for big data and advanced math. Now, let me start out with the first section, abstract algebra. And I want to try to provide a kind of cheat sheet for every one of the major sections. There's a little bit of a decoder ring here, if you will. The bottom line on this is that when you're building data workflows, that is automation plus teams, leveraging open source for big data, the bottom line there is that if you can leverage the abstract algebra in terms of how your code is structured, there are potentially exponential cost savings. And we're seeing this in large case studies such as Twitter, eBay, LinkedIn, others. It really helps in terms of cutting down latency, and that speaks to the bottom line for real-time analytics. It also cuts down bottlenecks, which would be showstoppers. And it's largely about building libraries in a team context. So to go into that, you may have heard the term monoid thrown around a lot with relationship to big data. Frankly, getting into the math papers talking about this kind of abstract algebra, the papers are really concise. If you are a mathematician, they're great to be able to read them, but they're almost devoid of context. And that's the thing that I find lacking. That's what we're trying to correct. We're trying to bring in more of the historical context, the business use case, etc., in contrast to what you would see in these kind of math papers. Here's actually a really good one called Intro to Semigroups and Monoids by Peter Clark. I like this paper. It's really well written, but again, it's not the kind of thing I'm going to put in front of a business audience. So instead of that, to break it down, here's a kind of cheat sheet. And this explains most of what you need to know about monoids and abstract algebra for big data. The idea is that if we start out with a set of things, think of a large collection, a large set of things. And in a very simple case, we'll say we have a lot of integers, a lot of numbers to add together. Say we have a billion of these numbers. Well, if we can start adding some definitions to the set and the operations that we use, we can come up with categories. And these categories have special properties that can be leveraged by the compilers, by the teams, etc. That's what we're driving to. So if we start out with a set of things, and we can show that we have an operation that we can apply to any two of the elements in the set, and then we get back another element in the set, that's a property called closure, and that defines a category called a semigroup. So as an example, if we had a billion integers and we have the operation addition, we can take two integers, add them together, get another integer, and we have this property satisfied in terms of a binary associative operation with closure, just adding two numbers together. Now, if we can also say that we have something called an identity element, that is to say if you take the number 3 and add the number 0 to it, you get back the number 3. So we call 0 an identity element. That's really important working with big data because there's a lot of sparse data in there. So the 0 elements, the identity elements, become very, very useful to leverage. If you take a semigroup and you add an identity element to it, you get a monoid. Now, if you have an inverse and you add that to a monoid, then you have a group, et cetera, et cetera. This whole category is something called magma. Frankly, I went through this in grad school, and I just learned that term recently. I always thought magma had to do with lava. But again, this is about, if you will, compiler hints. It's about leveraging abstract algebra to make your code really efficient in a team context. So as an example here, if I have several integers to add together, I can put the parentheses in different places. I don't care as much where the parentheses have to go. I still get the same result. That's the associative binary operation. And also the identity element, using 0 in this case with integers. It may seem kind of trivial to be adding integers together, but think about this. What if it was a billion elements of, say, customer profiles? Actually, that'd be a great case. I have a billion customers. But what if there was some other kind of complex object? Being able to take these and aggregate them together, that's the bottom line. It gets really difficult to do at scale, especially when there are real-time requirements. So that's what we're trying to mitigate the risk of doing that, if you will. And the real approach towards this, what's really paying off, is to leverage functional programming. So a little bit of history on that. Functional programming traces back, 80 years or so, going back to the 1920s, 1930s. Haskell Curry and Alonzo Church and others were working on combinators, working on lambda calculus. What they were trying to grapple with was the question, what can be computed? And it's interesting because this is decades before they actually had digital computers available, but they were trying to work out the math in advance. And they came out with an excellent body of math called lambda calculus that we leverage today. Rolling the clock out a few decades into the 70s, John Baucus led the team that created the Fortran compilers at IBM. So he definitely knew a lot about compiler theory, about large-scale applications of compiler theory and building programming languages, but he was struggling with moving away from a single processor. He was struggling with how can we parallelize workflows, create programs that could take advantage of, say, multi-core. In the 70s, we didn't really have those. I mean, mainframes had some multi-cores, but we didn't have the kind of processors that we have today. So he was really setting the stage for contemporary functional programming compilers. He came up with a language called FP, and it leveraged the work from Church and others in terms of lambda calculus, of how to bring in abstract algebra, let the compiler do algebra about the code. Now, rolling the clock out a few more decades, in 2007, Chris Wenzel was working at what's now Thomson Reuters. He was hanging around what became the Hadoop project and trying to evaluate that to see if he could leverage that kind of open source project for building custom search engines for Thomson and enterprise context. His takeaway was it was going to be difficult to get enough Java developers, enterprise Java developers, to work with MapReduce directly. So he introduced an API called Cascading. It was introducing functional programming inside of a Java API. So it's kind of a veneer. And it really had a lot of these artifacts of abstract algebra. It's really leveraging that. It's about being able to take, for instance, different functions and compose them together. And it's almost like stacking Lego blocks, if you will, composing these functions together. But you build up pipelines from them. You define the business logic of your workflows by building up these pipelines. And in turn, because of the mathematical properties, it has a lot of excellent information, metadata for the compilers to take advantage of that and make these nicely parallel to run on a Hadoop cluster. Twitter took this work, Cascading, a couple of years ago. On their ramp up towards IPO, Twitter introduced a new language called Scalding, which is a Scala API for cascading. And it's a functional programming language, and they have since reworked most of their revenue apps based on Scalding and also help evangelize this at other companies. It's an excellent project. It's kind of a case study for what we're presenting here. So the big idea in terms of computational thinking is that by leveraging an algebra of functions, we can let the compilers actually treat the code as data. And that allows for much better parallel processing. It allows for much more efficient code when you're working with a wide variety of data objects at scale. That's decomposition. Now, in terms of pattern recognition, if you can recognize that you're working in the context of aggregating a very large number of items, again, having that set of a billion numbers or a billion customer profiles, having to aggregate them, count them, sort them, find the uniques, whatever, these are types of aggregation. And if you can understand that the abstract algebra applies, this leads, number one, to the ability to build code libraries for much greater code reuse, again, the team context. It is actually what big data developers tend to do when they're writing Hadoop apps, even though many may not be able to articulate the abstract algebra part of it. It's what happens in practice. So by recognizing that, that's an opportunity. And in terms of algorithm design, this use of monoids, for instance, allows for much more efficient partitioning of data. And that way, the computational tasks can be spread across a cluster, again, parallelized. And that's important because when you're working with very large streams of data, you don't have the luxury of stepping back and putting it in the right order before you compute it. You have to take it as the order that it comes in. And so by having these mathematical properties, we relax a lot of constraints and can be much more flexible, cut down our costs drastically. So let's talk about that a bit. We'll move into kind of some case studies here about Twitter. When I use the word aggregation, that's what semigroups in abstract algebra is trying to address. Aggregation is a hard problem. If you've looked at SQL, there's a lot of aggregates that you might see in terms of reporting, count, max, sum, average, things like that. That works great in SQL if you're on one computer, one processor. When you start to have a cluster, a lot of the SQL abstractions become very difficult, very expensive. And so Twitter took a different tack. What they did was to create, again, I mentioned this Scalding project, and then inside of Scalding, there's a library called Algebra. A couple of the authors of both of these, Avi Bryant and Oscar Boynton, had some great presentations. I highly recommend this one from Avi Bryant. It's called Add All the Things, and he makes the case for leveraging the math to do aggregation at scale much, much more efficiently than what you could do with traditional kinds of database tools. Also, Algebra for Analytics by Oscar Boynton. This was at Strata earlier this year. And Oscar really makes the business case here. Lack of associativity increases latency exponentially. So if you want to do real-time analytics, you're going to be throwing a lot of resources at the problem unnecessarily. If you use the right math, you can make this effective. You can make it efficient. To show a case here, Oscar had a great example that I'm going to borrow. If you have a bunch of numbers to add together, you put them in a loop like you would in Fortran or other kinds of programming languages along that lines. If you take a bunch of numbers, you're going to have an order and cost. So if I take 16 numbers, it's going to cost me 15 steps to add them together. But if I define the addition as a monoid, I can run this in parallel. I can run it through essentially 4 steps instead of 15 for an order log n cost reduction. That's an exponential decrease in the cost. It means I can scale out, use a cluster to make this computation done horizontally, do the computation wide, and drastically reduce the number of steps. What that means is if I'm doing real-time analytics, I don't have to wait for a long batch window to add everything up. I can do this in a much less amount of time in process, in a streaming context. So in terms of computational thinking, we're talking about much less resources to be able to get the job done, much shorter time windows to be able to work with streaming, things like this. We don't have to anticipate partitions quite as strictly. The guarantees of monoids and semigroups make the code much, much more efficient. And that bears out in terms of data workflows. When we look at big data, there's been a kind of middleware evolving over the past decade. And here's a typical design pattern. You have a bunch of data sources. You go through some ETL. You do some data cleanup, and then you try to enrich the results with some kind of predictive modeling or things like that, and push out results to end use cases. It's a kind of graph. It's a way of representing the business logic of workflows, for enterprise data workflows. And workflows, I want to underscore the point, they're inherently about automation and people. So, we have a lot of aspects of workflows that we're seeing in this kind of middleware that have been evolving, that are very effective. And I've been trying to track this. An earlier book I did was called Enterprise Data Workflows with Cascading. But there's a number of other open source projects that have these kinds of properties, provide these kind of features. So here's a slide deck for a talk I've been doing to try and compare and contrast these different open source frameworks, showing what are the best of breed features, developing at least a preliminary scorecard to try and understand what they bring. I mentioned about algebra. It applies for multiple different frameworks that are leveraging this library, and it's really the basis for what Twitter is doing for a lot of efficiencies at scale. There's a great question here off the Stack Overflow where Oscar Boynton addresses why is Twitter going after abstract algebra. Now, if you want to see another project in which a lot of these concepts are coming together, Apache Spark is now the second most active project on Apache, open source project, and it also is able to leverage algebra. And a lot of these concepts about building a unified platform for workflows and leveraging the abstract algebra are very much inherent in Apache Spark, and I highly recommend that. There's 3 great presentations here that are listed. Okay, let me shift gears into a different area, Bayesian stats. So the cheat sheet here, the decoder ring, is that around the late 90s, I actually point to an inflection point, a sea change in about Q3 of 1997. We shifted gears as an industry. Prior to that point, we were looking at single data sets on a single server, a single processor, with a single model and a single analyst. And suddenly things changed. And after the late 90s, we saw a lot more work with commodity hardware in clusters. We saw ensembles of models being applied. It was much more interdisciplinary team context. So it shifted from one to many, if you will. Now, Bayesian stats are really good in that kind of context for big data. They're especially good for making judgments based on evidence where the business process is changing, where there's a lot of updated decisions. They're very good for leveraging the diversity in large-scale data as well. So to make that case, let me go back to a little bit of history here. Definitely Bayesian stats are probably not, if you took a Stats 101 course, they're probably not covered in that. It's kind of interesting. A lot of what we talked about was statistics up until the 19th century. A lot of people really thought that would mean vital statistics, capturing birth and death records, things like that. Now, there's a body of statistics that was developed in the late 19th century and in the early 20th century, and it tends to apply more for, say, insurance actuaries or, defending your PhD thesis. But it doesn't really work all that well in terms of a big data context. Oddly enough, there were efforts in statistics prior in terms of the 18th century, which are now much more applicable for big data, and that's where the Bayesian part comes in. So when I took stats in school, we talked about statistical data modeling. A lot of my peers became insurance actuaries, actually. And you would get a sample of data, and you would fit it to a known distribution, and you would perform significance tests to show how well your data fit the model that you'd chosen. And then from that point forward, you would make inferences based off the model, not so much off the data. And that worked, again, if you're an insurance actuary, or doing drug trials, or defending your PhD thesis. It's about really addressing an adversarial mathematician, if you will. It's great for testifying in court. Not so great for business cases. The problem is that this frequentist notion, the 19th and 20th century stats, are all about assuming a frequency of events, and that events are repeatable, and that you're making judgments in isolation. They're not so good if your business process is changing over time. And frankly, the frequentist side is kind of a luxury, because when we're talking about big data, we're talking about large-scale consumer problems or large-scale industrial internet problems where things are changing over time, and decisions must be updated. Thomas Bayes was a minister in Britain back in the 1700s. He was elected to the Royal Society because at the time, George Berkeley, the namesake for UC Berkeley, had attacked Isaac Newton and the work of Isaac Newton. So Bayes defended Newton, this whole thing about calculus and physics and whatnot. And he joined the Royal Society. Just shortly before his death, he wrote a paper about conditional probability. I've got a couple links there if you actually want to read it in the original early modern English. It's kind of a tough read. UCLA has a nice translation. But Laplace picked up this work and published it after Bayes' death. And it's now known as Bayes' theorem. And I'll just go over the highlights here. The idea is you want to drive toward a decision based off of prior context plus new evidence. So the decision you're driving toward, we call that a posterior. We want to calculate the probability of a hypothesis, H, given some evidence in data, D. Now that's based on two components. One is we have our previous business context. We call it a prior. And it's the decisions that we've done in the past. And that's the prior is the probability of H. That's the conditional part coming in. And then we have the new data, the new evidence, again, the update, if you will. And that's a ratio. On top of it, the numerator is called the likelihood. It's the probability of obtaining the data, the evidence, if the hypothesis is true. And that's normalized by the denominator of the ratio. It's the marginal probability of the evidence in data D happening in any case. So this is a way of taking both our previous decisions, that history, that context, and updating them with new evidence. So in terms of computational thinking, Bayesian approaches allow for more near-term decisions, incorporating evidence that's collected, your big data component, along with improving judgments that you've made in the past for future use. So as an example, I use this as an interview question. There's a customer experiment. So if you've read a book like Lean Startup, I used to run analytics at the company that Lean Startup was based off of. And we used to do a lot of customer experiments. So here's one for foodbartender.io. We've done some user experience, some user design, a few different customer experiments based on different designs. And we're watching how much people buy cocktails based on these different designs. So we've got these 4 experiments. We've got the number of visits and the number of purchases for each. And the interview question is, can you tell me which one of these experiments has the lowest purchase rate? So I'm really curious what you would think about that. I usually ask this in the workshops. And gosh, I'm going to spoil my interview question, but what this comes out with is a kind of a naive approach to this is to just divide the numbers, come up with a simple ratio. And in that case, it looks like experiment number 1 has the lowest ratio. 3 divided by 24 is 0.125. But then again, that experiment has the least data. So should we throw it out? Maybe it's not valid. Now, a Bayesian approach would be different on this. Again, Laplace was one of the co-author, if you will, of Bayes' rule. And here we're using a Laplacian approach to create what we call a point estimate. So if we have to make a decision based on a ratio, and we only have a little bit of evidence gathered so far, essentially we condition our judgment based on even money. We'll add a coin flip to this. The 1 over 2, as you see in that ratio there, 1 divided by 2 is 0.5. That's a coin toss. So what we're going to do is apply this thing called shrinkage, this coin toss, if you will, to adjust the ratio, and then we'll calculate some error bars, a confidence interval. What that produces then is, rather than the simple ratio, we've adjusted the ratio, and now if you look at the error bound bar, these 4 different experiments actually overlap each other. If you throw out one of them, you're possibly throwing the baby out with the bathwater. So the answer to the interview question is actually no. You can't say which one's lowest. And I've definitely had people who were in leadership positions in technology who sent me multiple pages of email about why the answer must be yes. So it's actually a pretty good question. The trick that we're doing there, again, is this Bayesian approach of shrinkage, of adjusting the ratio, if you will. If you don't know the answer just yet, you can apply some sort of prior. Now, the computational thinking there is that in terms of abstraction, point estimates, confidence intervals, these are a real good way to mitigate risk. You can think about them not just in the context of a user experiment, but a lot of different places where you're having to make a decision based on a ratio. It allows decisions to avoid the isolation that we talked about earlier and make much more quicker decisions that can be updated. Okay, so a different area of stats, very much related, was from Leo Bremen, was a stats prof at Berkeley, and he had a paper in 2001, highly recommended. It's called The Two Cultures, and it's chronicling a kind of sea change, if you will, in statistics being applied for data at scale. So a lot of the paper is based off of a movie called Rashomon, if you've ever seen it. It's a Japanese film from 1950 where there's a crime and 4 different witnesses at a trial are giving vastly different accounts of what had happened. Essentially, it's this. Bremen was looking at what was happening in the industry circa 2001, and it was after some of the early successes of e-commerce plays like Amazon and Google and eBay and whatnot. These were becoming apparent. And the notion there was that we had social context being recorded in terms of a web app or some kind of web app. We had the social context that was being dropped down into log files. We're collecting a lot of log files. That's the big data. And we're aggregating the log files. Again, the hard problem for abstract algebra is aggregation. And then we're feeding that into algorithmic modeling, machine learning, building recommender systems, building anti-fraud classifiers, etc. And then feeding the results of that back into the web apps to make them smarter and enrich the social interaction. So that's a lot of the epigenesis for big data and for bringing in machine learning at scale. They created a kind of feedback loop, if you will, a virtuous cycle. So that's what Bremen was talking about in the paper. And he also introduced the notion of, where he was talking a lot about ensembles. The idea that, especially with big data, you probably don't have just one pattern you're going after. You probably have a lot of customer segments that are interesting. So build up not just one data model, but a lot of them, and then allow them to vote together to come up with a more combined decision. This was borne out in the Netflix Prize. I've got links here from a couple of people who competed in that. So years later, we saw the teams that were winning the Netflix Prize leveraging ensembles and really proving the case for what Bremen had brought. Let me see the update here. Good. So in terms of computational thinking, the idea is, again, extending off of some of the Bayesian notions. Rather than making data fit a particular model, we can also build ensembles to describe structure within the data, leveraging the diversity of it. I like to think of this exercise of working with big data kind of like being a cinematographer, where you're trying to get the right camera angle on your data, leverage the computation to get the right shot. And that's what a lot of big data is about, and that's how you find the needle in the haystack, of getting that right camera angle, if you will. That's what we spend the money on these clusters for. Now, let me shift gears into linear algebra. Very, very applicable. This is where we're working with matrices. So the secret decoder ring on this is a lot of large-scale problems can be broken down into matrices. Once you have those matrices, you can apply a lot more parallel processing much more effectively. You can also leverage the abstract algebra, the monoids, if you will. So just as a refresher on linear algebra, I'm going to scoot through this pretty quickly. You'll have the slide. I've got a word problem here of Roadrunner versus Wile E. Coyote. And of course, Wile E. Coyote is trying to blow up Roadrunner in a trap. And we've got a little bit of a word problem that involves a system of equations. I can represent that as a set of matrices and vectors and come up with a solution. It's a way of leveraging a matrix as a kind of shorthand. I can have a number of equations, but I can represent them symbolically as a relatively concise problem. That's part of the beauty of linear algebra. Now, in this word problem, we've worked back and we've come up with how many seconds it takes Roadrunner to eat his seeds while Wile E. Coyote is chasing him, just before Wile E. Coyote narrowly misses him. It comes out to a solution of like 17 seconds. Kind of a fun problem. What it illustrates, though, is that you can leverage matrices to simplify how you represent a problem. Again, abstracting, if you will, leveraging computational thinking. You have much less moving parts. You can recognize the patterns much more effectively at a higher level of abstraction. And it also provides a really great context to leverage parallel processing. So when we talk about leveraging matrices and systems of equations, here's an example. There's an interesting way of breaking this down. I could say I have a matrix A and I have a variable x that's a vector and some values y. I can also talk about being able to do a matrix inverse. And this is where we get the notion of an identity matrix coming in, which you might recognize. An identity matrix is the identity that we talked about in monoids in terms of if the elements of the set are matrices. So there's kind of a bridge here between the abstract algebra and the linear algebra. And we apply that. We really leverage the semigroup structure. When we talk about large systems of equations, if you have n variables and n equations, you should be able to go after some kind of solution. If you have less than n equations, though, you don't have enough data. And so you end up having to optimize. Essentially, not enough of the data means you have too many possible solutions. So then we have to find which one of those are optimal. That's called an underdetermined system, and we'll show a case of linear programming for that. On the other hand, if you have n variables and more than n equations, you have too much data. That's a big data problem, typically. And in that case, we have to approximate an answer because there's no exact answer. So approximation, least squares, curve fitting, drawing a straight line through a bunch of dots. That's a typical kind of overdetermined system. So this is a good way of thinking about matrices and linear systems and recognizing that in some cases you have optimization, in some cases you have approximation. In fact, a lot of these algorithms will actually inject synthesized variables or tie down the values of variables to shift back and forth between approximating and optimizing. It's a nice technique. So I'm going to scoot through this one pretty quick, but here's a foo bartender example where we have to do some curve fitting. We've got some data points. We want to do a forecast, and there's there's a data there, and there's an equation, y equals mx plus b. I can turn this into a matrix formulation, and I can find the slope of my curve that's being fitted, my straight line that's being used for a forecast, and I can minimize the errors off that straight line. That's a typical kind of approximation. We use that in a lot of different cases. Now, in terms of graph theory, I know I'm going to shift gears here a little quick, but graph theory is very closely related to linear algebra. The idea is that a lot of problems in business can be reduced to graphs. In terms of marketing funnel, in terms of online marketing and sales, you can build up a graph. In terms of anti-fraud, very, very large-scale graphs. obviously social networks, a lot of kinds of supply chain problems and routing problems, they're graphs. Now, an interesting thing is if you have a graph, you can generally get to a sparse matrix. And then you can start to apply the linear algebra for the parallel processing. So when we do this, the linear algebra applied for graphs, a lot of times you'll hear a couple of terms, eigenvector, eigenvalue. It's a way of finding a stable point in the system, if you will, and then we can leverage those stable points. There's a lot of great applications for this. In the book and video, we go into much more detail. But one thing is you can take an image and stretch it or reshape it. So if you're using Photoshop, you're using eigenvectors to do that kind of scaling and rotation. Another case is you can do image recognition on faces, face recognition, basically having eigenvectors to compose building blocks for faces. Another way is to measure graphs. What's the diameter of a graph, for instance? It's a way of getting metrics and being able to do some inference about large-scale graphs. And there are some excellent frameworks for working with this. One that I would point to, this is actually, as I understand, being used in production by eBay. There's a way of taking, you can go from a graph to a matrix, as I mentioned before. Once you have a really large matrix, sparse matrix, one of the things you can do is split the matrix into chunks and then process those, say on Hadoop or Spark or some kind of parallel processing, process those in parallel on commodity hardware using open source, and then take the results and put them back together in parallel. Another thing that I like to point to is this from University of Florida. It's kind of a museum of sparse matrices and graphs. And they look like alien deep-sea creatures, but they're actually test cases for evaluating new algorithms work. It's a pretty fascinating read, though. I definitely recommend the link. So the idea with graphs is I have a simple graph here. Generally speaking, I can go from a graph into a matrix. Once I've got a matrix, I can apply all kinds of magic with linear algebra. And for instance, here I can find the eigenvalues of that matrix. And now one of the great things about graphs is that I can, when I get it into a matrix formulation, I can do a thing called factorizing it. I can do a matrix factorization. A very popular one is called SVD, singular value decomposition. It's a way of building recommender systems out of a matrix. Essentially, I can take a matrix here, matrix N, and split it into 3 other matrices to recreate it, regenerate it. And it has some special properties in that I'm using the eigenvectors and eigenvalues to build these other 3 matrices. But those matrices are set in a way such that I have ordered in the, sorry, let me go back here. In the middle matrix there's a sigma. And the most significant components, if you will, the most significant singular values describing this matrix are up to the top left. The least significant are to the bottom right. So what I can do is actually lop off from the bottom right and shrink this whole system down, essentially reducing it down to its essential structure. That's one way of customer segmentation. That's one way of a recommender system, et cetera. But it's a way of exposing the structure in a graph by leveraging the matrices. It's what's called dimensional reduction. And the problem being there that if we work with a lot of data, we may have thousands of dimensions. People can really only make judgments in 3 or 4 dimensions at once. You can't have intuition beyond that. But yet we're faced with problems that have thousands of dimensions, and we typically want to reduce them down. And so here's a couple of steps. You could start out with data, say, as a graph. Try to validate insights by using some graph query engine would be a great approach. And then from there, if you have insights, be able to leverage it by converting the graph into a sparse matrix, run some factorization on a commodity cluster, and then adjust it down by using an approach like singular values. It's a way of representing the structure. Again, getting the right camera angle. So we'll reinforce this kind of computational thinking throughout the video and the book, is getting that right computational approach to getting the right camera angle on the data. And okay, let's get into the last section here before we get to questions. Optimization. The cheat sheet, the decoder ring on optimization is that at the end of the day, machine learning is a subset of optimization. And optimization is sort of the devil you know. It's about supply chain, it's about routing problems, it's about maintenance schedules, it's about pricing models, et cetera. These are optimizations. And thus, machine learning can really apply with big data for these kinds of problems. At the end of the day, it's mostly a matter of what we call vector quantization. I'll come back to that, but it's what the clusters are performing. So I'm going to take the case of, say, IoT and industrial internet because they're very interesting. They're on the horizon. These kinds of use cases are surfacing now. They're orders of magnitude larger than what we've seen with social networks. So for instance, in terms of heavy machinery, they're probably not going to be concerned about building social networks. They're going to be optimizing supply chain for billions of dollars. And I think it has huge impact and significance because we're seeing IoT kinds of use cases throughout industry. We're seeing enormous data rates jumping up, again, orders of magnitude beyond what the social networks have had to contend with. And I think there's a lot of opportunities there because the abstract algebra, the graph theory, the linear algebra really comes into play. I've got a link here for a great overview of machine learning. It's from Pedro Domingos at U Washington, and it's a great way of representing machine learning as a subset of optimization. One type of optimization that's very popular is called linear programming. So if I have a number of constraints on a problem and I have some kind of function that I want to optimize, it's a pricing model and I want to optimize revenue. I have my constraints in terms of my materials, my labor, etc. I can represent this as a linear programming problem. And the thing is, I can turn it into a set of matrices and vectors and essentially solve it by introducing some artificial variables. We call them flat variables. I can convert a hard constraint problem into a system of equations and solve it that way. And this is great. In terms of computational thinking, we can decompose a complex optimization and we can transform it into a much simpler problem, system of equations, and thus be able to solve a very large scale number of variables and constraints. So Foo Bartender, for instance, has a problem with a pricing model. We want to try to optimize revenues for next quarter. We've got some numbers in from our costs from last quarter. There's 3 different drink categories we're going to try to optimize for our sales target. So as a quick example, I can build up a revenue model based off of some of the numbers here. I state this as inequalities, as constraints. I have some costs down here in terms of ingredients and salaries and delivery. And I can state this as equations. I can convert it into a matrix, and then I can convert it into a linear programming problem. If you want to see some of the code for how this kind of thing gets solved, it's pretty straightforward. It really matches what you would do when you're talking about the problem in words. But this one here is fun. You actually run it, linear programming problem. It comes out with the fact that, okay, we're going to boost our sales of pre-prohibition drinks. Basically 1/3 of our sales targets will be there. Liquid nitrogen drinks, 2/3 of our targets. And the freshly muddled, they're too expensive to deliver, so we're going to drop them all together. And the model pops out that we're going to end up having a forecast of $367K net revenue on approximately $850K costs for a 30% operating margin. Not bad. Okay, let me close up here on optimization. A lot of what your clusters are doing at the end of the day is some kind of vector quantization. Gradient descent is a very popular kind of approach for optimizing models, machine learning, etc. And there's a great video from Google about how they do deep learning at Google, and again, leveraging a lot of gradient descent. Jeff Dean has an excellent video down there. An interesting thing, just kind of as an aside, Google and others are looking at these D-Wave machines, these kind of quantum computing approaches. And oddly enough, if you can take the hard problems in big data and represent them, as we've said, graphs into linear algebra and then vector quantization on the linear algebra, oddly enough, the major cost basis has exponential decrease. You can go from, essentially what we're doing currently drops down to a constant cost if the quantum algorithms work out. Google and others are publishing a lot about evaluating that. But it's a very interesting thing on the horizon. Now, as a data point, as a way of computational thinking, that's a good kind of pattern to be on the lookout for. There may be new kinds of computation that can really take over the heavy lifting. And so that's why we're trying to reformulate things in terms of functional programming clusters, etc. As a data point, Google recently partnered with Caltech, and they came out with this Minecraft plugin called QCraft. It's a way of doing quantum algorithms in Minecraft. I have a 10-year-old. 10-year-olds play Minecraft constantly. I'm sure as many of you know. But the interesting thing there is in the press release Google was making an aside that, hey, maybe some of those 10-year-olds right now will have a lot of facility with Minecraft using quantum algorithms, quantum physics, and who knows, maybe they'll be Google interns not too many years from now if the D-Waves pan out. So I want to give a high-level summary. Kind of a big idea about this is that we can organize data. We can leverage graph structures and probabilistic data structures and other things we haven't gotten into here in the webcast. It's much more formal than taking the ad hoc approaches of the early adopters in big data. And that's where you see case studies like Twitter and eBay, et cetera, really getting the exponential increase. So go from real-world data. Perhaps you can leverage something like graphs. From there, convert into sparse matrices, apply functional programming, abstract algebra, get a lot of ROI off of parallelism on clusters. At the end of the day, it's about optimization. And maybe someday we will have quantum computing, but until then, we have Minecraft. As follow-ups, and then I'll get to some questions here. Again, we've got the video coming just out now for Just Enough Math. We've also got OffCon coming up, and we'll be presenting this as a tutorial. That'll be in Portland on July 20th, and I'm really looking forward to that. That's a great show. There's some other calendar events coming up. Let me cut over now to some of the QA. Oh, great. Okay, we've got a number of different questions lined up. So let me jump into some of the questions here. First one up, do differential equations play a role within data science? Yes, actually, it's a great question. Differential equations, again, using some of the calculus. When you look at things like PageRank, it's a difference equation. And it's solved very efficiently on clusters by finding the eigenvectors and eigenvalues first and then reformulating it as a matrix problem. So it's a way of, instead of calculating differential equations, thinking of differential equations conceptually, but then solving it with the kind of techniques we're talking about here. Next question. I use a D-Wave quantum computer. Really? That's amazing. I wish I had one of those. We're trying to find out which algorithms actually work. Google doesn't have their QC working yet. Yeah, no, that's true. The D-Wave stuff is pretty speculative, but it's a thing to watch on the horizon. There have been a couple of great papers coming out about this, a lot of great presentations. Seth Lloyd at Google Santa Monica, MIT professor who specializes in this area. There's a great YouTube video about that. There have been a couple of papers, some positive, some a little bit more negative. We'll see where this lands. But yeah, it's not a done deal yet. Another question. When having solutions in linear algebra problem, when you have too many solutions, you approximate. Are you using some probability when you do that? Interesting. I didn't talk a whole lot about another chapter that we present. It's about probabilistic data structures. It's a way of, Twitter has the catchphrase, don't sample, hash. So there's a way of handling really large-scale streaming analytics by using hashing, essentially probabilistic data structures, something you might hear called sketch algorithms. And again, you can get incredible efficiencies. So yes, that is where the probabilistic approaches in these solutions come in. Another question. What's your comment on HP versus titanium? I'm not going to go into recommending processors too much. It's kind of out of scope here. We could have that as an interesting sidebar comment. Another question. What do we think of Wolfram, MATLAB, Octave? Interesting. I watch Wolfram. I'm a big fan of Wolfram Alpha, et cetera. And certainly a lot of the concepts that we're talking about in Just Enough Math, MATLAB ends up being sort of a canonical way, especially in academia, of proving this out. Running at scale is a different thing altogether. Usually MATLAB is not going to bring you to scale. But it's a great tool in terms of being able to prove it. Okay, I've got a lot of questions, so I'm going to keep going through on these. Let's see. Question. We've been using Bayesian and DST on models that evolve based on data. This has been around since the early 90s, and we did this at DEC in the 90s. Yeah, well, actually, yeah, this has been around for a long time. It's been around since the 1700s. Laplace was using it to game the lottery back in France in the 1700s. It's just that, there's really still a conflict between people who are in sort of a BI, business intelligence mindset, and people who are really grappling with more real-time systems, streaming systems for more contemporary kinds of data science approaches. That's the point I'm making. There is still a lot of discussion about this. Question. You mentioned ETL middleware for big data. I take it that big data ETL occurs pretty much instantaneously in memory. Is that correct? No, actually. ETL is a hard problem because you've got a lot of different types of data sources. They're coming from a lot of different directions, a lot of different kinds of frameworks. It's not an instantaneous kind of thing usually. There may be streaming where you do have near-time results coming in, and there's a lot of different approaches on that. Spark streaming is a great one that I've been working with. But ETL is just one part of the middleware that's evolving, and it's a hard and complex thing. It's what a lot of the Hadoop clusters and Spark clusters get used for. Here's a great question. Why Python and not just Scala? So, I've pointed to use cases that leverage Scala, like scalding, algebra, Spark, etc. And it's a great functional language in industry. I'm a big fan of it. Python, though, you can show a lot of these kinds of things, a lot of these aspects of advanced algebra for business use cases, and you can show it in a very simple context. So Python really is a functional programming language. You can use it that way. And we felt it was much more accessible if we were starting out from, say, a bar of Algebra 2 to jump into Python as opposed to jumping into Scala. But we also show how to shift between the two of them. Okay, another question here. Stochastic gradient descent considered more decomposed operation than other iterative algorithms. Yeah. Okay. So, this is a call out from a good friend and a student also. A lot of these algorithms that I've mentioned, it's pretty interesting because Jimmy Lin from UMaryland and Twitter makes the case that a lot of the algorithms that we use on these clusters, Hadoop clusters, etc., they're still based on code that was written as if we were working in Fortran. And there were libraries that were written decades ago that have been translated into other languages like Java, Scala. But they're still thinking of things in terms of Fortran do loops. So there are ways of going back to the math, decomposing the problem, being able to leverage the parallelism a lot better. And Jimmy Lin makes that point in his papers. There's a lot of money on the table, really. So there's a lot of reasons for leveraging the math as opposed to just jumping in and using the tools naively. Another question. What are the leading Python packages available to implement some of these concepts? Great question. I'm seeing a lot of uptick on enterprise adoption of Python. It's great for a team context. It can be parallelized using things like Anaconda and Memba, etc. Some of the leading tools, definitely Anaconda and that whole suite, scikit-learn, Pandas, Augustus. There's just a wealth of different tools that are available in the Python sphere. And it's a great, PyData is a great way of approaching data workflows. Last question here. Do you cover any of this in R? We don't really use a lot of R in the book. Certainly, Alan and I both do a lot of R in practice, and on our teams we see a lot of this. But in the book, we really wanted to focus on just clear, concise examples in Python. So we chose to go that direction. Okay, I think that covers most of the questions that we have so far. Let me see if there's any URLs that are lacking here. Here's one for Twitter open source. Here's a homepage if you want. Sorry. Here's my homepage if you want to sign up for a newsletter. A lot of these kind of concepts. I think I pushed the. I'm trying to click on all the links here. I think I'm almost at the limit. There's Alan's homepage as well. He's got some great slides, especially in the genomics area, big data. I'm going to try to click a couple of those here. Let me see. I think we've got almost all the URLs up, so I'll call that good. And I think we've got a couple more questions that just came in. Hey, here's a great question. Are there any workshops scheduled in Toronto? No, but I'd love to. And I'm doing some work in Canada. I lived in Vancouver for a while. I have a lot of family from Eastern Canada. I'd love to get up there. Definitely been doing some work in over the border in Detroit area. But please contact me. We'd love to schedule something for Toronto. Let's see if there's any other questions that we got. I think that's about all the questions so far. Thank you very much. I really appreciate the opportunity to present. And check out our video, check out our tutorial at OSCON, and we'll have the book out a little bit later this summer. Thank you very much.
thank you so much, Paco, for a really outstanding webcast today and for sharing all your knowledge and expertise with us.
Wonderful. Thank you, guys.
Folks that attended the webcast, we thank you for attending, and we hope you have benefited from it. And as you close out, folks, we want to let you know we did push out a code to you all in your group chat, a couple codes actually. So open that group chat before you leave because there's some codes in there to save you some money. First and foremost, it's on Paco's new video, Just Enough Math, and his book that he's got out with O'Reilly. So get the book, get the video, a lot more in there that can really help you with your day-to-day. And also, we did push out a code to save you on your registration for OzCon. So best pricing ends tomorrow. But with the code I gave you all in the group chat, or write this down, Webcast. The code is Webcast. You can save 20% on your OzCon conference registration. And we pushed out the links to Paco's talk as well and to the reg page. So we hope to see you at our flagship conference. All right. We thank you again for attending today. Thank you, Paco. This will conclude today's webcast. Goodbye, everybody.